So at this point, we talked about how we define our networks, and we talked about different cable types and different media types. Now we're going to talk about Ethernet standards. So when we talk about Ethernet, we're talking about 802.3, which is the standards that they built of how we operate a wired network. So Ethernet technology. Back in the 1990s, there was many different networks out there competing for market share. They had Ethernet, they had Token Ring, they had fiber distributed data interface, and many others that were fighting to become the way that networks are going to be done in the future. After all was said and done, really, it came down to Ethernet being the clear choice as the winner of these network media wars, and everything we do now is based off Ethernet. It's important that we understand how Ethernet works, including the needs for the standards, the speeds, and the distances, to understand how this is all going to operate in our networks. So Ethernet originally ran over coaxial cables. We talked about that in the last lecture. And eventually it migrated into those twisted pair, the unshielded twisted pair and the shielded twisted pair. So we have these things called thick net and thin net. And the reason why they're called thick net and thin net is because it was a thick network cable or a thin network cable. Very creative names, right? The thick network cable was a 10^5 connector is what it was called. And the way we read this is 10 is the megabits per second. The 5 is how far it went. It went 500 meters. That's why they called it 10^5. And this is just a thick coaxial cable that was used. Thin net, on the other hand, was 10 megabits per second, but could only go 185 meters. So generally we use thick net to connect the switches together, and then we use thin net to connect the machines together because they would usually be within a 200 meter range, which is why we call it 10^2, because it's about 200 meters being at 185. Because again, coaxial, if you remember, we have that metal braided shield, that eliminated some EMI, which allowed us to go further distances. Eventually, people started getting able to get the shielded twisted pair and unshielded twisted pair up into the same 10 megabit per second range as coax. And so we have 10^T. The T doesn't stand for the distance anymore. It stands for T for twisted pair cable. So 10^T was our Cat3 cables. They had a maximum speed of 10 megabits per second, and all twisted pair only goes 100 meters. Always keep that in mind whenever you're dealing with twisted pair cables. 100 meters is your max. So one of the things that we had to determine was how we were going to get onto the network. And Ethernet had to address that to figure this out. Was it going to be deterministic, or was it going to be contention-based? When we do things deterministically, what we're going to do is we're going to be very organized. So if we use something like a token ring, we use that kindergarten example, we're all sitting in a circle, and we pass the bear around. The person who holds the bear has the token. They're allowed to talk. We all take our turns and nobody speaks over each other. That's what we use with a token ring network. We're very deterministic. The problem with that is there's a lot of overhead in that. And if we pass the token, and I say, hey, I'm going to give everybody the token, they can talk for 5 seconds. Well, what if I give it to Nick and he has nothing to say? We wasted 5 seconds. Then I give it to Sarah and she has nothing to say. We wasted 5 more seconds, right? Then I give it to the other Nick and he talks for 5 seconds, and then we give it to the next person. But Nick had more to say. We have to wait till we get back to Nick for him to talk again. And so there's that problem with deterministic, where you're not being most efficient, even though you are being organized. And that's why Ethernet ended up going with what's called the contention-based model. It is very chaotic, though. Essentially, you can talk whenever you want, right? If we're sitting in the middle class and all of a sudden Nick just starts talking out, we all either can listen to him, or if he's talking over me, nobody hears either one of us, right? And so that becomes an issue. So you transmit whatever you want, but you can have these collisions. Now, generally in networks, we're going to try to avoid these collisions, but they do happen, and we'll talk about those here in a second as well. So what Ethernet does is they use a thing called CSMA-CD, and that stands for Carrier Sense Multiple Access Collision Detection. And so what happens is basically I'm going to sit there. If I'm about to speak, I'm going to listen to the wire, and I'm listening for that pause in the conversation, right? And so I listen and I go, there's a pause. Let me talk. So now we all have access. We can talk. Whoever starts talking first is going to be the one who's going to get heard, right? So I start talking and I say something. Well, what happens if you guys have been at a party and you're talking in a group, you're all saying you wait for that time to chime in your 2 cents, right? You got this awesome nugget of information you want to say, and you wait for that pause, and as soon as you hear that pause, you and the guy next to you both speak at the same time, right? And you have that collision of information. Well, that happens on Ethernet sometimes. You know, I want to say something and Sarah wants to say something, and we both talk at the same time. What should we do then? Well, we have a collision, so what we're going to do is we're both going to back off and go, oh, I'm sorry. We'll both pick a random time and then start talking again. And hopefully we didn't both pick the same random time, right? So what that looks like is this. We have this bus network here, right? And we're all on a shared bus, meaning we're all in the same collision domain because we're all sharing the same wire. In this classroom, we're all sharing the same air that we're talking in. And what happens is, if we both talk at the same time, we get a collision. And so what's going to happen is both these machines are going to pick a random time. The guy on the left chose 200 milliseconds. The guy on the right chose 300 milliseconds. After 200 milliseconds elapses, the guy on the left's going to start talking, okay? If he's done by 300 milliseconds, then the other guy will start talking too. If he's not, remember we had that carrier sense, we're listening for that pause in the conversation. If he doesn't hear that pause, he'll just pick another timer and wait, okay? And that way we can back off from that collision and move forward. And now we can communicate again the way we need to. So when we look at collision domains, if we're dealing with coaxial cable, everybody's on the same cable, that's one collision domain, okay? If we're dealing with Ethernet twisted pair, it's anybody who's on the same hub. So in this case, we have a hub and two machines. This is all one big collision domain, okay? Because they're both sharing the hub, because remember with hubs, everyone talks and everyone hears what's being said on the hub. Devices can operate at half duplex, which means if you think of an old walkie-talkie, that's a half duplex communication, right? I talk, you listen, or you talk, I listen. We can't both talk at the same time. With phones, we use full duplex communication. You can both talk at the same time, right? And both hear at the same time. But walkie-talkies can't. And so when we're dealing with something like this with a hub, we're going to deal at half duplex because I have to listen first and then talk, or talk and then listen. This is how we avoid our collisions. So switches, on the other hand, they increase our scalability of our networks because they create multiple collision domains. Because the switches essentially are a hub with a bridge on every port, they become having their own collision domain on each one. So in this case, we have 3 clients. There are 3 collision domains being shown. Each one's on its own collision domain. Because there's no chance of collision, switches can allow you to operate at what's called full duplex. I can talk and I can listen at the same time. Because again, there's nobody else who can talk on my port. It's just me. So this allows us to minimize our collisions and make it a lot more effective for us. So when we talk about speed limitations on networks, we're talking about bandwidth. It's a measure of how many bits we can transmit in a given second at a time. We call that BPS, or bits per second. Every bit is a binary digit. It's either a 1 or a 0. And if I can transmit, more bits every second, I have a faster network. That's my bandwidth. Each cable is going to determine the type of bandwidth capacity you're going to have on the network. So if I have Ethernet and I have 10 megabits per second, that's 10 million bits per second. If I have fast Ethernet, that's 100 megabits per second. Gigabit Ethernet is a gigabit, or 1 gigabit per second, also known as 1,000 megabits per second. 10 gigabit will be 10 gigs, and 100 gigabit will be 100 gigs. When we transpose that with the type of cables we're going to deal with, you'll see our 10 base 5 and 10 base 2, that was our old coax connections, are only 10 megabits per second. If I look at 10 base T, which was my first twisted pair, Cat 3, I could do 10 megabits per second, the same as a coax. When I went up to Cat 5, that was called 100 base TX, that's 100 megabits per second. So again, we got the 100 in the front, tells us how fast it is. Go to the next one, it's 1,000, tells me it's 1 gigabit per second, right? Now, if you notice TX, that's twisted pair. Anything that's not TX is going to be a fiber connection, whether it's LX, LH, ZX, or something else. For the A+ exam, you don't need to worry too much about the designations for fiber connections. If you go on to Network Plus, they're going to want you to know, if they tell you, hey, I have a 1000 base LH connection, that it's fiber and that it's single mode fiber and not multi-mode. For A+, you don't need to worry about that though. For us, you really need to focus on 3, 5, and 6. As far as our categories are 100, 10, 100, and 1000 megabits per second. Those are the ones you're going to see often. And again, remember with UTP and STP, those twisted pair, it's 100 meters of length. Looks like was how much speed did it cost? Now just Yes. So originally we focused on getting our data up. And then once we went to fiber, it was data as well as, it was more important about distance. There are connections, like I said, up into the terabytes for fiber as well. This particular chart, I'm only showing you the stuff that's equivalent for local area networks, the 1000 base stuff. Yeah. There's actually charts of charts and tons of different cable standards depending on the distance and the speed you need. Terabyte there. You have best internet. So if we have a brand new data center that's been wired with all Cat6A wiring, the technician has been tasked to immediately install and boot up an already configured mission-critical file server. Prior to turning on the server, the technician realizes they had bought Cat5e patch cords by mistake. What should he do? Should he install his Cat5e cable, boot the server, and then return and replace it later? Should he inform the customer and recommend temporarily using the Cat5e cable? Should he install Cat5e cable, document the installation, and leave the premises? Or should he inform the server that inform the customer that the server will be available as soon as a Cat6A cable is acquired? What do you guys think? Speed. Yeah, exactly. So if we have a 5e versus a 6a, we're really dealing with a speed difference. A Cat5e will deal with 1 gigabit per second. A Cat6a will deal with 10 gigabits per second. Can I use a slower cable on a faster network? Sure, it's just going to operate slower. So for us, what we'll do is we'll inform our customer and we'll recommend they temporarily use the Cat5e cable. That way I have time to go to the store, get the Cat6 cable, and then replace the cable, because replacing a cable like that will only take a couple of seconds and you have minimal downtime. So this way we can get them up and running right now, and then we'll improve the speed later.